Now let's discuss the last part of this course. It's Ziegler-Nick's tuning of PID controller. So the PID tuning is basically selecting the values of the gains of the three terms in the PID controller. So the nice thing about the PID controller tuning, the approach we will discuss here, we have no idea about the plant. You don't need to know the transfer function of the plant. In other words, you don't need to do the modeling part. Then how we are going to tune the controller or selecting the values of the parameters. So the first step is to test the step response of the open loop system. So let's assume we have a system. We do not need to know the transfer function of GS. Then we use a step signal to test the system. If the step response of the open loop system has a form like this, so this is the process reaction curve. So we call this part. So in general, the system may not respond very fast. It is usually the case for chemical reaction process. Then from the beginning, when the step signal is applied here, until the response, the system starts to respond, we call this time period the lag. It's also time delay. Then we model this open loop system by a transfer function, a first order transfer function with time delay. So TD is the lag determined by the time delay here. So A is DC gain of the open loop transfer function will be, if we use unit step signal, that will be the final value of the step response. Then tau is a time constant. It's a time from here to here. Then we calculate the slope. R is A over tau. We call it reaction rate. So based on the step response, we can approximate the open loop system by a first order system with time delay. Time delay. Now let's discuss how to choose the PID controller. If we can get the transfer function of open loop system based on the process reaction curve, Then this is the closed loop structure. We have the approximated open loop transfer function. Then how to design the controller. The controller, it will be in this form, different from the standard PID controller we discussed. Just KP, so then KP over KI, this will be the KI, and KPTD will be KD in the standard PID controller. So the design idea is to make the step response. So here it's not 1 and 0.25, they're not the real value. Okay, this is the final value of the step response. So it will be y-SS, it will be steady state. So you can consider this part as overshoot. So the basic idea, so the controller parameters are chosen so that the closed loop step response trending with a decay ratio of approximately 0.25. This means that the trending decays to a quarter of its value. If we assume value here is y-SS plus 1, then after a period of oscillation, its value decreases to 0.25, a quarter of the highest value in the previous period. So then it corresponding to the damping ratio in a standard second order system. The damping ratio is about 0.21. Then based on some simulations, so Bigler and Nakos suggested the values for Kp, Ti, and Td are given in this value. If we use a P controller, it's 1 over R L. So that should be L. L is the time delay. Then R is the reaction rate. If you use PI controller, that's the value for Kp and Ti. If you use PID controller, Kp, Ti, and Td. So if you use this parameter suggested in this table, so in the closed loop step response, so damping ratio is about 0.21. So the decay ratio is a quarter. So the nice thing about the PID tuning, you do not need to know the transfer function or model transfer function based on physics. So the next tuning approach is ultimate sensitivity method. So ultimate sensitivity method is different from the step response method. So here, instead of evaluating step response, we evaluate the amplitude and frequency of the oscillations. at the limit of the stability, so rather than the step response. So the idea is we work on the closed loop system, not the open loop system at the beginning. Again, we assume we have no knowledge about the process. We don't need to model the process based on physics. So what are we going to do? We have the reference input. It could be a step signal. Then what we do, we increase here. We use a P controller, a proportional gain. So we increase the proportional gain until the system becomes marginally stable. As we mentioned that if the P controller, the value of P is very large, it may make the system unstable. Okay, it's caused the system to cause the instability of the system. So if we keep increasing the P controller, the gain of the P, if the system becomes marginally stable, then its response will be continuous oscillation. So we keep increasing the proportional gain. Maybe at some point, the output of control signal is limited by the saturation of the actuator. Then we keep a record of the value Ku and the period of the oscillation. Then let's call the period Pu. Sorry, the period is from, if it is the period from here to here, it's a Pu. So this is the Ku. Then there'll be ultimate gain Ku. Ultimate period Pu. Then we can choose optimum gain of the PID controller. If you use P controller, the Kp is half of Ku. If you use PI controller, you choose Kp and Ti according to these formulas. If you use PID controller, these are suggested values for the parameters. So experience suggested that the closed loop response, usually the Ziegler-Nichols tuning rules provide acceptable closed loop response for many systems. But to make sure the step response has a desired performance, you may need to iterate the process several times to yield satisfactory control performance. But Dickler-Nichols tuning rules give you the initial value for the PID controller. Sometimes some fine tuning may be needed.